Hello, I'm Aduk Prabhu and welcome to Lesson 4 on the Combinatorics course. Today, we're going to be talking about counting techniques. So now there's many different counting techniques and we're going to go over the basic ones like casework, where you split stuff into cases and solve them individually, complementary counting, when you count what you don't want and subtract that from the total, and constructive counting, where you build the counting up. We're also going to deal with ways to deal with overcounting, like how to deal with repeated elements, pairs of items, and symmetries. So let's start with the basic casework problem, just to get an idea of how it works. The figure to the right represents a road map between the four villages labeled A, B, C, and D. The arcs indicate paths between the various villages. How many ways are there to go from A to D along the paths, if you can only move left to right? So the first main thing you gotta notice is that there's two ways you can go. You either go A to B to D, or you go A to C to D. So let's count the ways you can go from A to B to D. So how many ways are there to go from A to B? 4. How many ways are there to go from B to D? 3. How many ways are there to go from A to C? How many ways are there to go from C to D? So now, how many total ways are there? 12 plus 10 is 22. And we split a relatively harder problem into just 2 multiplications and an addition. 22. So we got a different problem. On the island of Mumble, the Mumblean alphabet has only 5 letters, and every word in the Mumblean alphabet has no more than 3 letters in it. How many words are possible? A word can use a letter more than once, but 0 letters don't count as a word. So I guess then you split it into 3 cases. Either it has 1 letter, 2 letters, or 3 letters. So, how many ways can it have 1 letter? Well, there's 5 letters, or 5 options for the letters. How many ways can you have 2 letters? Well, there's 5 options for each letter, giving you 25. How many ways for 3? 5 options for 3 letters, giving you 125. Now, if you just add these all up, you just get 5 plus 25 plus 125, which is equal to 155 words. So, the inhabitants of the island of Mumble decided to expand their alphabet to the standard Roman alphabet. But they still limit their words to 3 letters or less for some reason, and they insist that all letters contain the letter A at least once. How many 3-letter words are possible? So I'm going to solve this in 2 ways, one with casework and one with complementary counting. First, let's solve it with casework. You have case 1, where the words look like A, and then some random letter. Then you have case 2, where the words look like with a random letter in between. And finally, you have case 3, where there's only one A. Sorry, there's 2 A's, but they are in the format. Okay, that's how many ways there can be 2. Remember that these cases are just for 2A's, and we're going to have to count 1A's and 3A's afterwards. How many ways can it be like this? There's 25 different ones, because this can't be A, or also be a 3 thing. So there's 75 different ways to have 2A's. 75 for 2A's. What about 1A? Then in that case, this would be a star. We would have this be a star, and this be a star. There's exactly 625 ways for each of these, which gives you 3 times 625. Or 1875. Finally, what if they're all A's? There's only one way, so plus 1. Adding all of these up, you get 1951. Now we're going to come back to this problem, except instead we're going to use complementary counting. But first, let's go into a different complementary counting problem. It's kind of switched, so sorry. How many 3-digit numbers are not multiples of 7? Well, that sounds kind of annoying. Like you go 1, 2, 3, 4, 5, 6, and you would count it like a list, except you have to skip 7. So that's kind of weird. Instead, we can count the total number of 3-digit numbers and take away the multiples of 7. How many total 3-digit numbers are there can be really easily counted in a list. You have 1, 2, 100, 101, all the way to 999, which is 900 numbers. Now, how many multiples of 7 are there? The smallest one is 15 times 7, which is 105. And the largest is 994. Dividing the entire thing by 7, you get 142 and 14. 142 and 14, how many numbers are between them? You get 129. And subtracting 129 gives you the problem, gives you the answer. 128 gives you the answer. Gives you the answer. 772. I forgot that this was 15. That's why. Now, the Smith family has 4 sons and 3 daughters. How many ways can there be seated in a row of 7 chairs, such as there are at least 2 boys next to each other? Well, that would mean it looks something like this. Boy, girl, boy, girl, boy, girl, boy. Okay? So that means there's this one case, which can be arranged in 4 factorial times 3 factorial ways. And the total number of ways you could arrange that is 7 factorial, which gives you 5,040 minus 144, which is 4,896. In this problem, or these two problems, you kind of see that a way to tell that complementary counting is going to happen is how many are not, or how many at least. So now let's go back to this problem. The inhabitants of the island of Mumble decided to expand their alphabet to the standard Roman alphabet, but they still limit their words to 3 letters or less. And this time we're going to try to reach it through complementary counting. And this is going to be a lot easier. How many ways can we have a 3-letter word? And then we just take away whichever ones don't have any A's. So you get 26 cubed, 3-letter words, minus how many ways can I have no A's? Well, each of them have 25 options because all of them accept A's, so you get 25 cubed subtracted. And you might actually realize that last time you got and you realize that they're equal. And that's actually a cool algebra fact. So yeah, that's nice. And if you actually compute this, you get the same answer, 1951. But this time we managed to solve it in one line instead of a lot of cases. So now let's go to constructive counting. How many 3-digit numbers have exactly 10? Well, we could do this as a casework using a method similar to a problem like this. But let's try to do it a different way. Let's do it with constructive counting. We've already seen some problems like this in previous videos, so let's go. We have 3 digits, and the 0 can be in one of these 2 digits. So there's 2 options for the 0. And no matter where the 0 is, you have 9 options for this, and you have 9 options for the other one. So you get 2 times 9 times 9, which is equal to 162. So therefore, there's 162 3-digit numbers that have exactly 10. Okay, how many sequences x1, x2, all the way to x7 can be formed, which all the x of I integers are greater than 0 and less than 6, and no 2 adjacent x of I are equal? So how would we construct such a sequence? Well, if we have 5 choices for the first number, like 1, 2, 3, 4, 5, the next number can be any of the choices except 5. So that would be 4, and so on and so forth for the rest of the 6. So you get 5 times 4 to the power 6. You go compute this and you get a pretty big number, 20,480, which is the number of possible sequences. So note that we have taken a constructive approach. We asked ourselves, how would we build this such sequence? And then the answer is like obvious. We just kind of multiply everything. And this is really good for problems where it makes sense, like how we would construct such a sequence. So now, let's go on with certain restrictions. How many ways can I arrange 3 different math books and 5 different history books on my bookshelf if I require a math book on both ends? So let's deal with the restriction first, because if you do it afterwards, it's going to be kind of hard to complementary count. So if we get something like math book, and then this kind of blend of 5 history and 1 math, and then we have another math book at the end. So there's 3 ways for this math book to be picked, times 2 ways for this math book to be picked, and then this is kind of just how you arrange 6 elements, so 6 factorial. So you get 6 times 6 factorial, or 4, 3, 2, 0. Now let's revisit the Smith family again. And this time, we're going to have a restriction. The Smith family has 4 sons and 3 daughters. How many ways can they be seated in a row of 7 chairs, such as all 3 girls sit next to each other? So there's 5 basic configurations. which go something like G, 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 B, 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 and so on and so forth. Instead of counting all that, let's call all the G's have to be next to each other. So let's just call it a big G and call it like a Supergirl block. And instead, now we got big G, and then the boys, and you get one boy, the big G, so on and so forth. And the girl can be in any of the, you can actually arrange this as 6 elements now. So you get, sorry, you can arrange this as 5 elements now. So you get 5 factorial, and the girl block can be arranged in 3 factorial ways because there's 3 girls inside it. So now you got 5 factorial times 3 factorial, which is equal to 720. How many possible distinct arrangements are there of the letters in the word dog? So now this is like, not any restriction anymore. It's just like we have repeated elements and we're trying to still find the number of permutations. So how many possible permutations are there? Well, it's just 3 factorial. 6. Well, what about we choose a harder word? Ball. You would think immediately it's 4 factorial. But then you realize the L's are the same. So if you just switch the L's, it's still the same situation. So how many ways can the L's be like switched around? 2 ways, which is computed by 2 factorial. So you get 4 factorial over 2 factorial, which is equal to 12. How many distinct arrangements are there of the word papa? Well, there's 4 factorial, but the p's can be switched in 2 factorial ways, and the a's can be switched in 2 factorial ways. So you get 4 factorial over 4, or 6. Now, let's go to counting pairs. Now, a nice problem that I like to start with is a round-robin tennis tournament consists of each player playing every other player exactly once. How many matches will be held during an n-person round-robin tournament? So, each player is playing against n-1 other players. So you might think that, well, just multiply this out, that's your answer. But then you kind of count everybody twice, because you count 1 playing with 7, let's say they have numbers, and 7 playing as 1 as 2 different scenarios, even though they both only occur. Like, they're both the same, and therefore there should not be. And exactly, there's 2 pairs of that, so you divide it by 2. And you get the formula n into n-1 into 2. So, another problem, compute the sum 1 plus 2 plus 3 plus 4 plus 5 all the way to 100. So let's kind of build this up. What is A? A, the answer is 1 plus 2 plus 3 plus 4, which is equal to 10 if you compute it. B is 15. C, you count it, you add it, you get 55. And it's kind of annoying, like, especially for 10, you have to add 10 numbers. You have to go, like, 1 plus 2 plus 3, so on and so forth. And that's kind of a lot of work. So, let's try to find a general formula for it. So, let's say we have a sum, which is equal to 1 plus 2 plus 3, all the way to n-1 plus n. Okay? And let's actually just flip it in reverse. You get s is equal to n plus n-1 plus n-2 all the way to 2 and then 1. So if you add these entire things, you get 2 times the sum is equal to n plus 1, and this happens n times. So you get n plus 1 into n. And you get the sum is equal to n into n plus 1 over 2. We check it on the following numbers. 4 times 5 over 2, 10. 5 times 6 over 2, 15. 10 times 11 over 2, 55. So now let's compute the sum of the first 100 numbers. 100 into 101 over 2 is 5050. So now you got the same answer for the last two problems. Why do you think that is? Let's try to find like a relation. Well, instead of doing that, we can say number the players, like 1 through n. Say player 1 plays all the players other than him. They're like really similar. All the players other than him. So n minus 1 players. The player number 2 plays all the players other than player 1, because that's already been counted. So you'll get plus n minus 2. And you get the sum of the numbers from 1 to n minus 1, which, as we already know, is n into n plus 1 over 2. N into n minus 1 over 2. So now let's go with counting with symmetries. So symmetries is when you can kind of overlap different situations, but that kind of sounds confusing, like, what? So symmetry is like when you can, where situations look very similar. Like in this, you have two identical ones, basically. It's just the entire thing's just rotated a little bit. That's symmetry. Hard to explain, but let's solve this problem to understand it better. How many different ways can 6 people be seated at a round table if 2 seating arrangements are considered the same, if for each person the person to his left or right is the same in both arrangements? So basically these are the same. And there's many arrangements, and like it doesn't matter what the exact positions are as long as they're relative. So let's just say A is the topmost one. And now there's 5 people to arrange. So that's just 5 factorial, which is 120. So basically what we did is we just found that it had a rotational symmetry. And we just fixed something to get rid of that symmetry. And now everything else is distinct, and we counted that. And that's basically the summary of counting techniques. We went over many different things like casework, complementary counting, constructive counting, permutations, but elements are repeated, pairs of items, and symmetries. Thank you for listening. Hope you learned something. And have a nice day. Bye.